Okay, so let's find r minus r prime, because remember what we need is the magnitude. So we're first going to get r minus r prime, and then take the magnitude so that we'll have this script r in the denominator. So we get r minus r prime. This is for the regular charge. So I have x minus a I hat, right? I'm just subtracting I hats and I hats, j hats and j hats, k and k. So I have x minus a I hat plus y j hat plus z k hat. So that's the vector, but potential is a scalar, so we only need the magnitude for that, and the magnitude of r minus r prime. We take each component, add them up, and take the square root. So I get x minus a squared plus y squared plus z squared, and all of that is under the square root. And so this is the sort of script r for this first term over here. Right? Same thing for the image charge. So now I do the same thing, but all I have now is just the image source point. So I have kind of x minus b I hat plus y j hat plus z k hat. And again, I only want the magnitude. So I square each component, add them up, take the square root. And so I get x minus, and at this point, I might as well plug in what b is. So that's going to be x minus r squared over a squared plus y squared plus z squared. And all of that is under the square root. So that's my script r I. And so that looks like a whole lot, but really the only reason we did all that is just so that we can easily get the denominator for these things, right? Finding r by itself, finding r prime by itself, those are a lot easier. And so if you go through that procedure of using I hat, j hat, and k hat, that will kind of walk you along in the steps of finding r minus r prime, the vector, and then taking its magnitude by squaring each and getting this magnitude here. So now these two square roots I can put in the denominator of my formula here. So let's plug that all in. The potential due to these 2 point charges, which is going to give us our sort of substitute problem, is 1 over 4 pi epsilon naught. And we're going to have the regular charge divided by the script r for the regular charge. So we're going to have x squared, x minus a squared plus y squared plus z squared, and all of that is under the square root. So that's the first term. And now the second term has the image charge, but we know that we're going to use this formula for the image charge, right? It's not just minus q, there's this r over a out front. So I'm going to include that right off the bat. So instead of adding, we're going to subtract r over a times q, and then we divide by our script r formula here that we came up with. Plus y squared plus z squared, and all of that is under the square root. And so at this point, we're kind of done. This is the answer, right? It's a little ugly there, but you could plug in any value of x, y, or z and get a value for the potential. As long as we know what r and a and q are, we can get all of those quantities. However, it's important that we check the boundary conditions, because if it doesn't satisfy the boundary condition, then solving this problem does not help us at all with solving this problem, right? We need to make sure that the boundary conditions are the same. And if they are, then I can say that these two are equivalent and this solution is the same as the previous solution. And so we should check the boundary condition. The second boundary condition is actually a little bit easier to check first. So as x, y, or z goes off to infinity, then the potential has to go to 0. And that's sort of obviously true, because if I plug in either X or Y or Z or any combination of them, if any of those gets really, really big, then I'm going to have, Q divided by a big number, and that's going to be 0, right? So the X, Y, or Z, the potential going off to 0 as we get to infinity, that definitely works because all my X's, Y's, and Z's are in the denominator. However, checking the first one, that's really the more important one, because that this idea that at R, when we are at a point where little r is equal to big R, then B should be 0. That is unique to this spherical shell kind of problem that we've been looking at. And so I'm just going to show one example of how that's true, just to kind of make sure that we understand, sort of where that's coming from. And so let's just pick a point that we know is on the shell and make sure that that's going to be the case. So rather than picking like a weird spot, I'm just going to pick the point x equals capital R, y equals 0, z equals 0. So that will certainly be on the surface of the sphere. So if we look at our picture right here, that's kind of this point right here. So it's on the surface of the sphere, and we're just going to show and make sure that that's going to give us a potential of 0. And so I'm just going to plug that into our formula here. What we get when we plug in x equals r, y equals 0, z equals 0, we still have our 1/4 pi epsilon naught. And I have q divided by, I have r minus a squared plus 0 squared plus 0 squared. We'll simplify that in a second. Minus r over a q over r minus r squared over a squared plus 0 squared plus 0 squared, not z. Right, so we're plugging in our values here, and now I can sort of simplify this a little bit. Obviously, the zeros go away, and so I can pull a q out as well, just because that's less stuff for me to write. And so what I get is 1 over square root of r minus a squared minus 1 over, now I have this r over a, and what I can see here is I have an r in both of these terms, so I can pull this out, and I get 1 minus r squared over a squared, something like that. And so what I have here is a square root of r squared, that's just r, and so this guy cancels with this guy. I can also distribute this a, and let's see what we get for that. I'm holding off on these square roots for a second, just because there's an important point we want to keep track of. So if I distribute that, what I end up with is a minus, I pulled out, let me just adjust this. I pulled out that value of r, which means now there's only one r left in here. So from up here, I had 1 r in the first term, 2 in the second term, and so I pulled out an r and squared it, and that's where that went. So now I end up with something like this, and it looks like this doesn't quite match up because one of them is r minus a, and the other one is a minus r. But we got to be careful about that because I'm squaring it and then taking the square root. And so these are sort of magnitudes here, right? It's just the value of r minus a squared, the value of a minus r squared, and then we square root that. So these are both positive numbers, and that's going to be the same value, meaning that it's completely equivalent for me to say that this is 1 over r minus a squared square root minus 1 over r minus a squared square root. So it's important not to just jump right to that square root, because this point here where you're squaring it and taking the square root, that sort of removes all the minus signs here. And so because of that, these guys will cancel out and I get b is equal to 0. And that's exactly what we should get there, right? So here's a situation where we had a problem where I had this sort of complicated spherical shell that was grounded. So that gave us kind of a strange boundary condition. But if we use these two formulas here for the image charge and the location of the image charge, then we can put an image charge in place and solve this problem. And even though we had all kinds of r's and r primes, we still get the same boundary conditions. So the solution we got here is also the solution for this problem instead. Okay.